We have looked at the core principles of space engineering, from handling extreme environments to the complex process of building and operating a spacecraft. Now, in this final video of the series, we are going to look forward. What's next for space engineering? Space engineering is a field of constant innovation. Here are some of the most exciting and critical areas driving its future. First, In-Situ Resource Utilization, or ISRU. This is the revolutionary concept of living off the land in space, aiming to use resources found on the moon, Mars, or asteroids instead of launching everything from Earth. For example, extracting water ice could create rocket propellant or breathable air, dramatically reducing mission costs. Next, there is in-space manufacturing. Imagine building large antenna or entire habitats directly in orbit or another celestial body, which reduces the need for large structures to fit inside rocket fairings and allows for on-demand repairs. This technology is also important for future lunar bases and Martian settlements. The rise of small satellites and constellations is already reshaping the space industry. Thousands of tiny CubeSats and nanosats work together in vast constellations to provide global coverage for multiple applications. This approach offers redundancy, faster development cycles, and lower launch costs, though engineers are now focusing on managing such massive numbers of satellites and preventing collisions. Deep space exploration continues to push the boundaries of engineering. Sending missions to the outer planets or beyond the solar system presents immense challenges, including long communication delays demanding greater spacecraft autonomy. Power generation becomes more difficult, making advanced strategies and similar technology more important. Radiation shielding also becomes more critical for instruments and potential human crews on multi-year space travel. Space debris mitigation remains a critical challenge. With more and more objects in orbit, the risk of collisions increases. While engineers design new satellites to deorbit responsibly, there's a growing need for active debris removal technologies to safely capture and remove large defunct objects from orbit, cleaning up the space environment for future generations. Finally, the vision of lunar and Martian habitation is moving from science fiction to engineering reality. Building and sustaining long-term human presence on other worlds requires solving complex challenges like creating robust habitats, developing closed-loop life support systems, and integrating ISRU capabilities to make settlements self-sufficient. This will require new advances in robotics, construction, and environmental control. In addition to these uncrewed missions, the world is also focusing on human spaceflight. Adding humans to the equation brings a whole new level of complexity and unique demands. The most fundamental requirement for human spaceflight is creating a miniature Earth environment. This is the job of the Environmental Control and Life Support System, or the ECLSS. Its goal is to maintain a breathable atmosphere, comfortable temperature, and manage waste. Humans are far more vulnerable to the space environment than electronics. Two key engineering challenges here are radiation protection and managing the effects of microgravity. For radiation protection, which can cause potential DNA damage and increase the risk of cancer in humans, engineers use passive shielding with dense materials like water or the spacecraft structure itself. They also design dedicated storm shelters within habitats for safety during solar flares. Active shielding using magnetic fields is still in research phase. Mission planners carefully select trajectories to minimize time spent in high radiation areas. For microgravity countermeasures, engineers design specialized equipment to combat bone density loss, muscle weakening, fluid shifts caused by prolonged weightlessness. This includes exercise equipment like treadmills with harnesses and resistance devices, which astronauts use daily. Additionally, human-centric design ensures proper handholds, foot restraints, and ergonomic layouts, allowing astronauts to work efficiently without gravity, reducing fatigue and injury. These engineering solutions directly support human health and performance, transforming a hostile environment into a functional living space. Looking ahead, human spaceflight aims for far beyond low Earth orbit. Engineering is critical for enabling long-duration missions to the moon, Mars, and beyond. You don't need me to tell you that the entire field of space technology is growing. However, what I'm here to tell you is that the space industry is looking for professionals from various different disciplines. That you don't have to only look at the sky at the end of a long day and imagine how beautiful and rewarding your career would have been if you could work in space exploration. Because right now, it is the perfect time for you to join this industry, and you don't have to shy away just because you don't have an aerospace engineering degree. Take a look at the link in the description of this video. I've created a course called Transfer to Space specifically for you to find out how you can use your skills to build a portfolio that will align with the space sector. It will teach you about the new age space industry, how you can map your skills correctly, and how you can launch your career in space. Enroll at the link today and start your journey. Let me know your feedback also on this space engineering series in the comments, and stay subscribed to this channel for more space videos. Thank you.